The idea of a perfect square is just that. I have a perfect square. So I'm going to draw some squares here. And notice they're just getting a little bit bigger as we go. And when we go back and look at these squares, if I have a square, both dimensions are the same. And then the area or the space that fills it up would be 1 times 1, which is 1 squared, which is 1. In the second case, let's just make this 2 by 2 square. So the area then is 2 times 2, which is 2 squared, or 4. And in the last case, we have a square that is 3 by 3, which would be 3 squared, or the area would be 9. Then we have an idea of a perfect cube. So now we can see things in 3 dimensions. So I have a 1 by 1, but now I have this section that goes back. So when I look at this, it's 1 by 1 by 1, where the volume of this is 1 cubed, which is 1. Making a little bit bigger cube, we'll say this cube is 2 by 2 by 2, and finding the volume of that, you multiply the 3 dimensions, you get 2 cubed, which is 8. So what we're going to be doing with perfect cubes and squares is relating them to exponents. And these exponents are what we call fractional exponents. So what we're going to be looking at is a to the 1 over n, which says the nth root of a. Now when we talk about a root, we talk about a beginning. So when I go and look at 16, I'm thinking of that as an area of 16. And I want the square root of 16. Notice that the square root, because it's a 1/2 power. The square root of 16 is asking you, what's the root of the value that gave you 16? And that would be 4. In the second case, I'm asking you for the square root of 9. My area of my square is 9. I want the root or the length of the side, and that would be 3. Here I want not the square root, but I want the cube root. And how do I know that? Because I have a 3 there. To write it, it is the cubed root of 8. So it's saying you have a cube, and the volume of the cube is 8. What were the dimensions of the sides? They would be 2. And the last one, the 4th root, and I can't draw the 4th dimension, but the 4th root of 16, it's saying what multiplied by itself 4 times would give you 16, and that would be 2. So that n is actually undoing a power. It's undoing the power. We call it an index. And if you think about the index, it's located in the denominators. Denominators cancel numerators. And we call these things radicals. This little symbol is a radical, and that is the square root. A radical could be a cube root, and so forth. So multiplication. If I have the nth root of a times b, I can look at the nth root of a times the nth root of b. And I can do that because if you recall, the nth root is 1 over n in the exponent position, and that means multiplication. If I have division, again, I can look at the nth root of a separate from the nth root of b, because again, we're looking at the nth root, which is a power, which means exponent, which in turn has the operator of multiplication. Multiplication and division work together. However, addition and subtraction do not. If I am looking at the nth root of a plus b, it is not the nth root of a plus the nth root of b. It can't be. The nth root is multiplication. Multiplication and addition do not work together. Now, our fractional power could also have a numerator. So if I want to rewrite this, if you recall, the nth power in the denominator is called the index. Here's my base a, and then I have a power of m. So all I did was we see a to an m power, and then we're going to take that to the nth power. And so there's two things happening here. M is the exponent, and n is the index. So they actually start to cancel each other. If I look at 3/2, we don't want to write it as 1.5. That doesn't mean much. I'm going to dissect it down. It says I want 16, and I want to cube it from the 3 in the numerator, and I want to take the square root of that. Well, I don't know what 16 cubed is in my head, but I do know what the square root of 16 is, and then with that, I can cube. The square root of 16 is 4. 4 cubed would be 4 times 4, which is 16, times another 4, which is 64. In this case, 27 is my base. It looks like it wants to square 27 and take the cube root of 27. Well, one of these you'll be able to do. 27 squared you could do, but it would take you some time. So I'm going to do the cubed root of 27. The cubed root of 27. What number times itself 3 times would give me 27, and it looks like that value is 3. So the cubed root of 27 is 3. The end result said square that 3, and I get 9. 8 to the power of 4/3. So the exponent is 4, the index is 3. And notice if they were common factors, they would cancel each other. I don't know what 8 to the 4th is. I could figure it out, but it would take me more time than I want. Cubed root of 8 is 2. 2 to the 4th power is what I have remaining, which means 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. 64 wants me to square it. Again, I don't know what the square of that is, but I do know the cubed root of 64 is 4. 4 times 4, 3 times is 64. So the cubed root of 64 is 4. I'm left to still square that, and I get 16. So what would happen if these exponents actually would simplify? For example, if I had 8 to the 4/4, that would be asking me to take the 4th root of 8, raise it to the 4th power. Well, that's just going to be equal to 8. Let's try one here. 8 to the 3/3. So that's saying cube 8 and also take the cube root of 8. So let's take the cube root of 8 because I know that's 2. 2 cubed is 8. So if you have a fraction in the exponent, it just works like your regular fractional operations. You can reduce that fraction if you want to make the problem a lot easier.